Unit 4. Social Interactions. Previous models of choice did not depend on others' decisions. Individuals motivated by self-interest can produce outcomes that are beneficial for society. Example, entrepreneurship, innovation. However, self-interest can also be harmful to society. Why do these problems arise? What can we do about it? In this unit, we use the tools of game theory to model social interactions and explain social dilemmas. Social dilemma, a situation in which actions taken independently by self-interested individuals result in a socially suboptimal outcome. Example, traffic jams, climate change. In this unit we see that social dilemmas occur when people do not fully account for the effects of their actions on others. Examples are tragedy of the commons. Common property or common resources are often overexploited. Free riding. One person or party bears all the costs while everyone enjoys the benefits. We learn how can altruism and government policy resolve social dilemmas. Game theory. Key concepts. Social and strategic interactions. Social interaction, a situation involving more than one person party where one's actions affect both their own and other people's outcomes. Strategic interaction, a social interaction where people are aware of the ways that their actions affect others. Strategy, actions that people can take when engaging in a social interaction. Game. A game describes a social interaction. Four key components of a game are 1. Players. Who is involved in the interaction? 2. Feasible strategies. Actions each player can take. 3. Information. What each player knows when choosing their action. 4. Payoffs. Outcomes for every possible combinations of actions. Example, crop choice. Two farmers decide which crop to specialize in. They interact only once, one-shot game. The four components of the game are 1. Players in the game are Anil and Bala. 2. Feasible strategies. Each farmer has two strategies to choose from, to plant rice or cassava. 3. Information. Each farmer does not know what the other chose. 4. Payoffs. Depend on market prices and quality of land. Anil's choices are the rows of the table and Bala's are the columns. We call Anil the row player and Bala the column player. Figure shows the payoffs, the benefit to each player associated with the joint actions of all the players. For Anil and Bala, in each of the four hypothetical situations, the incomes they would receive if the hypothetical row and column actions were taken. Since their incomes depend on the market prices, which in turn depend on their decisions, we have called this an invisible hand game. In figure above, we represent the payoffs for Anil and Bala using a standard format called a payoff matrix. A matrix is just any rectangular, in this case square, array of numbers. The first number in each box is the reward received by the row player, whose name begins with A as a reminder that his payoff is first. The second number is the column player's payoff. Let us look at the optimal decision-making process by understanding some important terms in game theory. Best response, strategy that yields the highest payoff given the other player's strategy. Dominant strategy, a best response to all possible strategies of the other player. Does not always exist. Dominant strategy equilibrium, an outcome of a game in which everyone plays their dominant strategy. Crop choice example. Best response. If Bala grows rice, Anil's best response is to grow cassava because if he plants rice, his payoff is 1, but if he plants cassava, his payoff is 4, and 4 is greater than 1. If Bala grows cassava, Anil's best response is to grow cassava because if he plants rice, his payoff is 2, but if he plants cassava, his payoff is 3, and 3 is greater than 2. For Bala, if Anil plants rice, the best response is to plant rice because if Bala plants rice, the payoff is 3, but with cassava, the payoff is 2, and 3 is greater than 2. If Anil plants cassava, Bala's best response is rice once again, since Bala's payoff is 4 with rice, but 1 with cassava, and 4 is greater than 1. Dominant strategy. So Anil's dominant strategy is to grow cassava. Bala's dominant strategy is to grow rice. Dominant strategy being defined as a best response to all possible strategies of the other player. Does not always exist. Dominant strategy equilibrium. When Anil and Bala each play their dominant strategy, the outcome is cassava rice. So cassava rice is the dominant strategy equilibrium in this game. Resolving social dilemmas. The prisoner's dilemma, so called because when two prisoners are asked to either accuse their partner in being involved in the crime and get a lighter sentence for cooperating with police, or deny their involvement and get a higher sentence if the other prisoner accuses them, end up accusing each other, even though if they both denied it, they would have been let go and would be better off. But not knowing what the other person will do, they end up accusing each other, since that is their dominant strategy. Prisoner's dilemma, a game with a dominant strategy equilibrium in which playing the dominant strategy yields lower individual and total payoffs compared to other strategies. Pesticide example. Both farmers choose to use the more harmful pest control T. Imagine that Anil and Bala are now facing a different problem. Each is deciding how to deal with pest insects that destroy the crops they cultivate in their adjacent fields. Each has two feasible strategies. The first is to use an inexpensive chemical called Terminator, T. It kills every insect for miles around. Terminator also leaks into the water supply that they both use. The second is to use integrated pest control, IPC, instead of a chemical. A farmer using IPC introduces beneficial insects to the farm. The beneficial insects eat the pest insects. If just one of them chooses Terminator, the damage is quite limited. If they both choose it, water contamination becomes a serious problem, and they need to buy a costly filtering system. Payoff matrix on the slide describes their interaction. If Bala chooses IPC, Anil has a higher payoff if he chooses T, 4 compared to 3 with IPC. If Bala chooses T, Anil has a higher payoff if he chooses T, 2 instead of 1 with IPC. So in this case, the dominant strategy for Anil is Terminator. Similarly, for Bala, the dominant strategy is T. Thus the dominant strategy equilibrium is Terminator, Terminator. Socially optimal outcome is not achieved. They would have higher payoffs with IPC, IPC. Why did we predict this outcome? This outcome is the result of the assumptions being made. We look at the assumptions and then consider the impact of changing them on the outcome of the game. We assumed 1. Players only care about their own payoffs. We will see what happens when we introduce social preferences. 2. Nobody could make players pay for the consequences of their actions on others. We will introduce repeated games, social norms, and peer punishment. 3. Players could not coordinate their actions beforehand. We consider how a change in the rules of the game, institutions and policies affects the outcome. Learning about preferences. To learn whether people care only about themselves or are altruistic and care about other people. Economists sometimes use lab and field experiments to learn about preferences. Lab experiments, benefits, can control participants' decisions and their outcomes, can create a control/treatment group for comparison. Results can be replicated, can control for other variables. Field experiments, benefits. Lab experiments may not predict real-world decision making. Field experiments provide a more realistic context in which people make decisions. Social preferences, altruism. Social dilemmas arise when players only care about their own payoffs. However, in experiments, many players show altruism by choosing the dominated strategy. Altruistic preferences affect the shape of indifference curves. Anil's indifference curves are vertical when he is selfish. If Anil finds 10,000 rupees, the feasible frontier shows all the ways in which this money can be split. Anil can keep it all as at point A, give all of it away, or split it in a manner given by the feasible frontier. What Anil does depends on his preferences. If Anil is selfish, Anil's indifference curves are vertical. His utility is highest on the curve that lies furthest to the right. Anil will choose to be at point A and keep all the money, 10,000 rupees, to himself, since that is the furthest indifference curve Anil can reach given the feasible frontier. If Anil is altruistic, his indifference curves are downward sloping. If he derives utility from Bala's consumption, he has downward sloping indifference curves, so he may prefer an outcome where Bala gets some of the money. Indeed, with downward sloping indifference curves, Anil will choose the combination B, since that lies on a higher indifference curve than point A. In this case, Anil will keep 7,000 rupees and Bala will get 3,000. Introducing social preferences changes the outcome of the game and may resolve situations involving social dilemmas. Resolving the prisoner's dilemma. Pesticide example. If Anil is somewhat altruistic, then his dominant strategy is I instead of T. The two axes in the figure represent Anil and Bala's payoffs. The 4 points are the feasible outcomes associated to the strategies. If Anil does not care about Bala's well-being, his indifference curves are vertical, so Ti is his most preferred outcome. He prefers Ti to II, so should choose T if Bala chooses I. Ti is also preferable to TT, so Anil should choose T if Bala chooses T. If Anil is completely selfish, T is unambiguously his best choice. When Anil cares about Bala's well-being, indifference curves are downward sloping and II is his most preferred outcome. If Bala chooses I, Anil should choose I, since II is on a higher indifference curve than Ti. Anil should also choose I if Bala chooses T, since he prefers IT to TT. The curve going through TT would be below the one going through IT. Social preferences. Other types besides altruism. Inequality aversion. Disliking outcomes in which some individuals receive more than others. Reciprocity. Being kind/helpful to others who are kind/helpful, and vice versa. We evaluate whether others have been kind or helpful according to social norms. Common understanding of how to act in situations when one's actions affect others. These motives affect outcomes in the public goods game and the ultimatum game. Repeated games. We have so far looked at one-shot games. Better outcomes can arise in repeated interactions due to social norms, reciprocity, and peer punishment. Behaving selfishly in one period has consequences in future periods, so it may no longer be a dominant strategy. Public goods game, farming example. There are a group of 4 farmers. Each farmer decides whether to contribute to the public good, example irrigation project. Contributing has a personal cost, but everyone benefits even if one person contributes. This is an example of prisoner's dilemma game with more than 2 people. Not contributing, free riding, is a dominant strategy. Imagine the cost of contributing to an irrigation project is $10. As long as one person contributes, the benefit to all 4 farmers is worth $8 to each farmer. On the graph, the number of farmers contributing is shown on the horizontal axis. The blue bars show one farmer Kim's payoff if she contributes. The red bars show Kim's payoff if she does not contribute. If Kim alone contributes, her cost is $10, but the benefit is $8, so Kim's payoff is negative $2, shown by the blue bar. Her payoff is 0 if she does not contribute, since in this case her cost is 0 and benefit is 0 if no one else contributes either. If one other farmer contributes, Kim's cost is $10, benefit is $16, $8 times 2. So Kim's payoff if she contributes is $6, $16 minus $10, shown by blue bar. But if she does not contribute, it is $8, shown by red bar. If 2 other farmers contribute, Kim's cost is $10, benefit is $24, so her payoff if she contributes is $14, $24 minus $10, shown by blue bar, but $16, $8 times 2 if she does not contribute. In each case, the red bar shows her payoff is greater if she does not contribute. If 3 other farmers contributed, Kim's cost would be $10 and the benefit $32, so her payoff if she contributes is $22, but if she does not contribute, it is $24. Each farmer will realize that it is better to try to get a free ride. The dominant strategy for each farmer is to not contribute. If each farmer chooses not to contribute, the project will not get funded and they will all be worse off, individually and collectively. They could each have gotten a payoff of $22 if each had contributed, whereas now the payoff is 0. Great economist Elinor Ostrom, 1933 to 2012, a political scientist, as a co-recipient of the 2009 Nobel Prize in Economics. First woman to get Nobel Prize in Economics, economists believed that resources could not be used efficiently and sustainably under a common property regime. Thanks to Elinor Ostrom, this is no longer a dominant view. Ostrom developed simple game theoretic models in which individuals have unorthodox preferences, caring directly about trust and reciprocity. And she looked for the ways in which people faced with a social dilemma avoided tragedy by changing the rules so that the strategic nature of the interaction was transformed. She worked with economists to run a pioneering series of experiments confirming the widespread use of costly punishment in response to excessive resource extraction, and also demonstrated the power of communication and the critical role of informal agreements in supporting cooperation. Reciprocity and social norms. In public goods experiments, people were happy to contribute as long as others reciprocate. Contributions differ according to social norms. Figure shows the results of laboratory experiments that mimic the costs and benefits from contribution to a public good in the real world. The experiments were conducted in cities around the world. In each experiment, participants played 10 rounds of a public goods game similar to the one involving Kim and the other farmers that we just described. In each round, The people in the experiment, we call them subjects, are given $20. They are randomly sorted into small groups, typically of 4 people who don't know each other. They are asked to decide on a contribution from their $20 to a common pool of money. The pool is a public good. For every dollar contributed, each person in the group receives 40 cents, including the contributor. In every country, contributions were positive, showing altruism. However, contributions declined in successive rounds as people realized other people were not contributing as much. In this case, in order to punish the free riders, the contributors reduced their contribution, leading to less money for the public good. This is the tragedy of the commons. Peer punishment. The ability to identify and punish free riders also increases individual contributions. In this game, after observing the contributions of their group, individual players could pay to punish other players by making them pay a $3 fine. For the majority of subjects, including those in China, South Korea, Northern Europe, and the English-speaking countries, contributions increased when they had the opportunity to punish free riders. The Ultimatum Game, a sequential game where players choose how to divide up economic rents, example cash price, is a good example of real-life situations involving strategic social interaction. Figure shows game tree. The game tree is a useful way to represent social interactions because it clarifies who does what, when they choose, and what are the results. We see that in the Ultimatum Game, one player, the proposer, chooses her strategy first, followed by the responder. It is called a sequential game, a game in which all players do not choose their strategies at the same time, and players that choose later can see the strategies already chosen by the other players, for example, the Ultimatum Game. Previously, we looked at simultaneous games, a game in which players choose strategies simultaneously, for example, the prisoner's dilemma. Suppose somebody finds $100 on the street. How might they split this money with a friend who was there when the money was found? The proposer's offer may be motivated by altruism, fairness, 50-50 split, inequality aversion, social norms, or reciprocity. These social preferences all influence our behavior, sometimes working in opposite directions. For example, if the money finder has strong fairness preferences but knows that the friend is entirely selfish, the fairness preferences tempt the finder to share, but the reciprocity preferences push the finder to keep the money. For example, if the proposer offers $20 and the responder accepts, the proposer gets $80 and the responder gets $20. If the responder rejects the offer, they both get nothing. What ends up happening depends on the social norms and the individual's preferences for reciprocity. If individuals care only about self-interest, then any offer greater than 0 will be acceptable to the responder, in which case proposer will probably offer 1 cent. Example: Kenyan farmers and US students. Offers are consistent with social preferences but also with expected payoff maximization. Experiments show that people are not entirely self-interested and all 1 cent offers tend to be rejected. To see how farmers in Kenya and students in the US played this game, look at the figure. The height of each bar indicates the fraction of responders who were willing to accept the offer indicated on the horizontal axis. Offers of more than half of the pie were acceptable to all of the subjects in both countries, as you would expect. A higher proportion of US students made offers of 30% or less than Kenyan farmers, and most of those offers would be accepted. The dark shaded area on each bar shows the percentage of offers rejected. Although the results in figure indicate that attitudes differ towards what is fair, and how important fairness is, nobody in the Kenyan and US experiments was willing to accept an offer of 0, even though by rejecting it they would also receive 0. Nash equilibrium, a set of strategies, one per player, such that each player's strategy is the best response to the strategies chosen by everyone else. In a Nash equilibrium, no player has an incentive to deviate unilaterally. Note, there may be more than one Nash equilibrium in a game. Here is an example with a different payoff structure. In this case, Anil's best response when Bala chooses rice is cassava. Anil's best response if Bala chooses cassava is rice. Similarly, Bala's best response if Anil plants rice is cassava. Bala's best response if Anil chooses cassava is rice. There is no dominant strategy and no dominant strategy equilibrium. There are two Nash equilibriums, rice cassava and cassava rice. They could end up with a payoff of 4 each or a payoff of 2 each. Once in equilibrium, no player has the incentive to deviate unilaterally because they would be worse off if they did that. If they talk to one another, they could get the better outcome, but in this example, we are assuming no possibility of cooperation or coordination. If they end up with the rice cassava equilibrium and a payoff of 2-2, now if Anil changes unilaterally to cassava but Bala stays with cassava, Anil's payoff will fall to 1. Similarly, if Bala changed from cassava to rice while Anil stayed with rice, Bala's payoff will fall to 1. So they might be stuck with a payoff of 2-2. If we change the rules of the game and allow some kind of social agreement, we can improve on the outcome of this game. Coordination issues. When there is more than one Nash equilibrium and individuals choose independently, the socially optimal outcome may not be selected, as we just saw. Society could be stuck in a suboptimal outcome since there is no incentive to unilaterally change one's action. Example: climate change. The two countries, China and US, have to choose between climate change policies to restrict emissions, restrict, or continue with business as usual, BAU. Outcomes depend on rules and preferences. Inequality aversion and reciprocity will result in two Nash equilibria here, restrict, restrict, and BAU, BAU, which include the social optimum. If the BAU-BAU equilibrium is chosen, then society could be stuck there. No one would choose to restrict because if the other country continued to do business as usual, the country that chose to restrict would end up with the worst outcome. An emissions treaty would produce the socially optimal outcome, restrict, restrict. Great economists, John Nash. John Nash, 1928 to 2015, completed his doctoral thesis at Princeton University at the age of 21. It was just 27 pages long, yet it advanced game theory, which was a little-known branch of mathematics back then, in ways that led to a dramatic transformation of economics. He provided an answer to the question, when people interact strategically, what would one expect them to do? His answer, now known as a Nash equilibrium, a set of strategies, one for each player in the game, such that each player's strategy is a best response to the strategies chosen by everyone else, is a collection of strategies, one for each player, such that if these strategies were to be publicly revealed, no player would regret his or her own choice. That is, if all players chose strategies that are consistent with a Nash equilibrium, then nobody can gain by unilaterally switching to a different strategy. Summary 1. Social interactions can be modeled as games. Players choose best responses to others' strategies. 2. Social dilemmas. Example, prisoner's dilemma can be resolved by social preferences, peer punishment, or binding agreements. The rules of the game also matter for outcomes. 3. Multiple Nash equilibria can cause coordination problems. Economic and political institutions can help achieve socially optimal outcomes.